Хорошо. Hi, today we continue our discussion of the most important properties of liquids. And I will remind you that the last time we started to consider some of the properties of liquids, and the first property was the fact that the liquid surface is always, this is the liquid, and the liquid surface is always perpendicular to the acceleration of free fall. And for this purpose, planets are spherical. And this is a good approximation to the shape of a planet. But if we take into account the rotation of a planet about some axis, the planet is rotating, then this rotation results in slight deformation of the planet's shape, and the planet's shape becomes an ellipsoid of revolution. That is something like that. Ellipsoid of revolution. It becomes flattened at the poles and bulging at the equator. So that was the first property of liquid. And we consider planet as liquid because actually most of the planet volume is liquid inside. And only a small crust of solid ground is on the surface of the planet where we live. The second property of liquids was the liquid pressure. Yes, we considered a vessel with liquid, and the pressure at some depth h in this point, the pressure was proven to be equal to the density of liquid, acceleration of free fall, and the depth of the point of consideration. This is a very important result which accounts for many phenomena. And I would like to solve a simple problem to illustrate this formula. Imagine you have a vessel with liquid and a thick tube, a glass tube, is immersed into this liquid. Say this is a water, for example, and the glass tube of the diameter of 2 centimeters is immersed into water. Certainly the water will go into the tube and the water surface will be here. What we will do in this problem, we will imagine that we pour some vegetable oil here, some vegetable oil, and the question is, how much oil can we pour in such a way that the oil doesn't mix with water in this vessel? Let this depth be 8 centimeters, the depth to which the glass tube is immersed into water. And so if we start pouring oil, the oil will gather on the surface, and as more oil is gathered here on the surface, it will press against water and the water surface will go down under the pressure of this oil. And so the problem asks what amount of oil can be poured here so that the oil doesn't go outside the tube and doesn't mix with water. Actually, if you pour some vegetable oil on the surface of the water, the oil will float on the surface and it will not mix with water. Such is the property of that liquid. And we know that the density of water is 1 gram per centimeter cube, and the density of oil is about 0.8 gram per centimeter cube. Is everything okay there? Problem. We know the density of water, and we know the density of oil, vegetable oil, and we know that oil doesn't mix with water. So the question is, how much oil can be poured into this tube if the tube is immersed into water by 8 centimeters? And by condition of this problem, the oil should not mix with water. So we pour oil here, and it presses against water, and the water level inside the tube goes down. And it should go down to the end of this tube according to the problem statement. So all this volume should be filled with vegetable oil. And we need to find the amount of oil. It means we need to find this height of oil column. We form some oil column here, and we need to find its height. So we understand that in the state of equilibrium, pressure at this point can be calculated as the pressure of water, because water is pressing on the oil, and also pressure at this point at the border between oil and water can be calculated as the pressure from the oil. So the pressure from the oil will be the oil density GH, where H is the height of the oil column. And the pressure of water at the same level will be equal to the pressure of oil at this point, and the pressure of water will be density of water, acceleration of free fall, and the depth of this level under the surface of the water, which is 8 centimeters. Well, we can denote this quantity by some character. Let it be L. So this is the condition of static equilibrium between the column of oil and water in this vessel. Due to this condition, we certainly may cancel G and immediately find the H, which is the height of the oil column, and the H from this formula will be L times density of water divided by the density of oil. And as we know, L, it's 8 centimeters, and the densities relate as 1 gram of per centimeter cubic water and 0.8 grams per centimeter cubic for oil. So after carrying out this calculation, we understand that the result will be 8 centimeters. So we can pour oil here so that the oil column will be 10 centimeter height. 10 centimeter height. H will be 10 centimeters if the tube is immersed in water by 8 centimeters. So this is the simple illustration of this formula for pressure inside liquid. Also, I would like to give you some more illustration to this formula. Suppose we have a submarine which is 100 meters below the water surface in the ocean. So this is the surface of water in the ocean, and somewhere 100 meters below there is a submarine. I will draw it as a round hull. Well, that is almost true if you consider the cross section of submarine. And suppose there is a small hole occurring in the submarine hull. Yes, the water pressure here will be calculated by this formula, and let's do it immediately. Now I will take the water density as 1,000 kilograms per meter cubic. 1,000 kilograms, 1 ton per meter cubic. That is the density of water times 10 meters per second squared. That is the acceleration of free fall, and the h is 100 meters. 100 meters. What do we have here? 1,000 times 10 times 100. That will give you 10 to the 6th power. Meters here and meters here and meter cube here will cancel. And what we have here is kilogram per meter per second squared. Well, that dimension, that combination of units doesn't seem to be promising. You don't recognize what is it. But what if we multiply numerator and denominator by 1 meter? And so here we will have meter squared. And so now we recognize that kilogram times meter times second squared is just 1 Newton. And so we will have Newton per meter squared. Newton per meter squared. 1 million newtons per meter squared. Well, that also doesn't make much sense if I try to put it into kilograms per centimeter squared. So 1 Newton, we have 1 million. 1 Newton is 0.1 kilogram force, just kilogram force. It's not mass, it's a force. And meter squared, 1 meter is 100 centimeters. If I take meter squared, then 100 should be squared. To understand how many centimeters are there, that will be 10 to the 4th power centimeters squared. And that will give me something like, yes, just 10 kilograms per centimeter squared. That makes sense because 1 kilogram per centimeter squared is known to be approximately 1 atmosphere. That is the pressure of 1 atmosphere of atmospheric air under the normal conditions, under the temperature of about room temperature. So 1 kilogram per centimeter squared is 1 atmosphere. And what we have here, 10 kilograms per centimeter squared, that is 10 atmospheres. That makes sense because it's well known that when you immerse into water, each 10-meter immersion will give you, each 10-meter depth will give you additional pressure of 1 atmosphere. So if pressure at the surface is supposed to be 0, well, we don't feel the atmosphere. We may subtract it. It's 0 on the surface. So if you go down to 10 meters below the water surface, the additional pressure will be 1 atmosphere. If you go down to another 10 meters, that is to 20 meters, that will be 2 atmospheres additional pressure. And here at the height, at the depth of 100 meters, the additional pressure will be 10 atmospheres. 10 atmospheres. And if you have water here at such pressure and a small hole in the hull of the submarine, then water will flow here at some velocity. And I would like to ask the question, what will be the velocity of that water jet? Actually, this is another problem. We will consider it right away. We will consider this problem right away and then return to discussing this situation. So this is a third, maybe considered as a third property of liquid. That is, if we have some liquid and a small hole in the vessel, then the liquid will flow away. It will flow away. And we need to calculate the velocity of this flow, of this water jet. Suppose we consider a small portion of liquid, which will have the mass delta mu, a small portion of liquid. Then this small portion of liquid will have a kinetic energy delta mu velocity squared over 2. Where does this kinetic energy come from? From mechanical law of conservation of energy, we know that if something gains kinetic energy, then somewhere some other kind of energy, some other sort of energy should be diminished. Obviously here, when we consider a vessel with water, if some portion of water flows out, then the surface of liquid here goes down inevitably, because liquid is incompressible. So if some volume of liquid goes down, then the surface will go down, and the mass of this liquid which flows away is exactly delta mu. If delta mu of liquid, the mass of liquid goes out, then the surface will go down in such a way that the mass of this vanishing liquid is equal to this mass, because liquid is incompressible. It's very hard to compress the liquid. It's impossible to change the volume of liquid. The volume is always the same. It's incompressible. So the volume of liquid which goes out here and the volume of liquid which is here is the same. And so if this volume was here, it had a potential energy of mass times acceleration of free fall times the depth of this hole inside the vessel with liquid, mgh. So the mass is now denoted as delta nu. So this water had this water layer, a thin layer of liquid, actually, yes, any liquid, not necessarily water. This layer of liquid had such potential energy, and when small mass went out, this potential energy was certainly is lost. It vanished. So the system of liquid in the vessel lost some potential energy, and instead of it, some kinetic energy emerged. So we may be sure that from energy consideration, energy balance will give us that the kinetic energy of this small mass of liquid equals the loss of potential energy of the liquid in the vessel. So considering this equation, we notice that we can cancel delta nu, and the velocity with which the liquid flows away will be equal to square root 2gh. 2 acceleration of free fall times the depth below the liquid surface where the small hole is in the walls of this vessel. So we have calculated the velocity with which the liquid flows out of the vessel. And if you remember well the formulas for kinematics, you will understand that this velocity coincides with the velocity of a body that falls freely from this height h down here. So you may drop a small body, or be it a droplet of liquid, or be it a small stone, it doesn't matter. You may drop it and it will fall down, and the velocity of this body here equals to the speed of water flow out of the vessel if the hole is at the same depth h. So that is just the velocity of the body falling freely in a gravitational field of the planet. So as far as the submarine hull is concerned, at a small hole in the submarine hull and the high pressure outside, like 10 atmospheres, and the water velocity here, water stream velocity will be, we have solved this problem, we have found the water stream velocity, and we can now calculate it. The only thing we need is to know the depth and the acceleration of free fall, which can be taken as 10 in the international system, and the h is 100 meters. And so the answer in the international system will be in meters per second. And so that will give us 1,000, 2,000, and the square root out of 2,000 is about, well, something like yes, that is the square root of 100 is 10. The square root of 100 is 10, and the square root of 20 is about 4.5, approximately 4.5. Because if you take 4 squared is 16, and 5 squared is 25. So 20 is somewhere in between. So that's approximately this way. And so that is 45 meters per second. 45 meters, that's the height of a 9-story building. That's the height of, why do I say 9-story building? It's more than 9-story building. It's about maybe 12-story building. And that's a large distance it's made in 1 second. So the water flow here will have huge velocity. It will be very strong water jet, by the way, very strong water jet, which will go into the submarine if there is a small hole in the hull. And this water jet, this high velocity, is ensured by high pressure outside of water outside. Well, that gives you some hint what may go on if there is a catastrophic development of events under the water. So, by the way, if the water flows at such high velocity, it will very quickly fill the volume of submarine. But the question is, will all the volume be filled with water? No, because there is atmosphere, and the atmosphere inside, the gas inside, will be compressed. Compressed to which pressure? To balance the outside pressure, the gas will be compressed to 10 atmospheres. And if the initial pressure was 1 atmosphere and the final pressure will be 10 atmospheres, then the gas will be compressed tenfold. The volume will diminish by 10 times. So the small amount of atmosphere will remain here, and then and all this volume will be filled with water, and such will be the development of these catastrophic events. If there is a small hole in the hull. Also, last time we discussed Archimedes forces, that is property number 4. Archimedes forces. Well, we understood last time that if we have a vessel with water and some arbitrary body is immersed into the water, then water or liquid pressure, any liquid, not necessarily water, any liquid will behave in the same way. The liquid pressure on the surface of this body will result in the net buoyant force, that is an Archimedes force, a net buoyant force that will be equal to the weight mg of the displaced water. The displaced water is the water in the volume of the immersed body. If we immerse the body into the liquid, then the liquid will be displaced by this body. So the volume of liquid inside the volume of this, the amount of liquid in the volume inside in the volume of the immersed body is called the displaced liquid. And so the Archimedes force will be equal to the weight of the displaced liquid. And the weight can easily be found. We need to calculate the mass of the liquid in the volume of the immersed body. So the mass of the liquid will be certainly the density of liquid times volume of the immersed body. So if we know the density of liquid and the volume of the immersed body, then we know the buoyant force, which tends to lift the immersed body upward. And certainly there is another force acting on this body, a force of gravity, which will be mass of the body mg. And the mass of the immersed body is denoted by capital M. If the force of gravity, if the weight of the immersed body is larger than the Archimedes force, the buoyant force, then the immersed body will tend to sink down to the bottom. If, to the contrary, mg is smaller than the weight of the displaced liquid, then the Archimedes force, the buoyant force, will be larger than the weight of the body, and the immersed body will tend to float up. So whether the body will sink down or float up depends on the comparison of weights of the immersed body and the weight of the displaced liquid. And certainly if the weight of the immersed body equals the weight of the displaced liquid, then these two forces will balance each other and the body inside the liquid will be in equilibrium. It will float inside without any tendency to sink or to float up. Such was the Archimedes force which we discussed last time. And now we consider the next question, the next question that will be called surface tension. Surface tension. Let's consider the surface of liquid, and let us think about the molecules which are here on the surface and the molecules which are inside the liquid. Liquid is characterized by the fact that molecules interact with each other, and this interaction is quite considerable. So this molecule inside the liquid is attracted by adjacent molecules and these forces of attraction act in all possible directions, and all they balance each other, and so this molecule inside is in the state of equilibrium. It doesn't tend to move anywhere, and if this molecule moves, only because that happens only because of thermal motion of molecules. But the forces acting on the molecule are balanced, and it doesn't there is no net force. Net force, an average net force acting on any molecule inside the liquid is zero. The average net force is zero. Well, the situation is different if we consider a molecule on the surface of the liquid. This molecule is interacting with the adjacent molecules, and this interaction is directed towards the liquid volume, and there is no interaction from outside. Therefore, some net force is acting on the molecule which is on the surface. The net force from other molecules of this liquid. And that means that if you want to take any molecule inside the liquid, and if you want to pull it up to the surface of the liquid surface, you have to perform some work against this force. You have to move the molecule against the acting forces on it. So you will have to perform some work. And that means that in order to create some surface on the liquid, you have to perform some work. It means that there is some surface energy inherent to this liquid, and every type of liquid has its own surface energy. This surface energy is usually denoted by a letter sigma. Sigma is, by definition, the energy of a unit area of the liquid surface. The energy of the unit area. So if the area differs from unity, then the total energy of the surface will be equal to, the energy of the unit area times the total surface area, total surface area of the liquid. The larger the surface area of the liquid, the larger will be the energy needed to create this surface. And this energy, which you need to create the surface of liquid, is associated with the forces acting on molecules, which inevitably result in the necessity to perform some work in order to pull molecules up to the surface. Any molecule tends to go inside the liquid because of the forces acting on it. And so in order to create surface, you have to perform work. So this quantity, physical quantity, has the dimensions of energy, which is measured in joules, divided by meter squared, which is the measure for the area of the liquid surface. If you look into this dimension, into this units of measurement, you may remember that joule is 1 Newton times 1 meter, divided here by meter squared. And what we obtain is Newton divided by meter. So this is the unit of measurement of force, and meter is the unit of measurement of length. So surface tension, surface energy can also be considered as some force applied to some unit length. We will discuss this later. But as this is some force applied to a unit length, then this quantity is called surface tension. Tension is related to a force, and sometimes it's called surface energy. So it may be called both surface energy or surface tension, and all this makes sense because the physical meaning of this quantity is both the energy of the unit area of the liquid surface and the force applied to a unit length. Unit length of what? We will discuss it right away. Let's consider a wireframe, a wire which has a U-form wire, a wire in the form of a character U, capital. We consider a wireframe and another piece of wire which is called a jumper. The jumper or a slide is in touch with these two wires and can easily slide along these wires. Let's consider such a simple installation. If you immerse this wireframe into a soap solution of soap in water, and then take it out, then you may create a thin film of soap solution, of a thin soap solution film here. So this thin film will have a surface which is directed, which is looking at you, and another surface on the opposite side. So there are two surfaces of this thin film of soap solution. There are two surfaces. And now suppose we move this wire jumper by a small distance. We move it here by distance x, and let the length of this section of wire be L. And if we move it here, we certainly apply some force because the soap film tends to reduce its area, as shows the experiment, as shows any experiments with soap films. Any soap film tends to reduce its area. So in order to increase the area of the soap film, you have to apply some force. And if using this force you displace or shift this wire jumper rightwards by some distance x, then you perform some work, which is certainly F delta x. And this work is done to increase the surface energy, the total surface energy, delta E, because you increase the surface of the soap film by this amount, and there is some surface energy associated with the liquid surface. And so if you increase the surface, then you increase the surface energy. And the increase in surface energy will be, in this particular case, sigma times L delta x. delta x. So this is the surface increase. If you shift the slide by the distance delta x. But the situation here is somewhat more complicated because we have not a single surface. There are two surfaces of this water film, soap film. There are two surfaces from two sides. And as there are two surfaces, then the force will be 2 times larger if as compared to the force needed to expand the surface of only one film, the single surface. If you compare two surfaces with the case of a single surface, it's obvious that when we have two surfaces, the total force should be twice the amount of the force needed to apply to a single surface. So we have here 2, because actually the area of the surface is not merely L delta x. This is the area of one surface, but there is another surface from another side of it, and so the area is twice L delta x. Well, from this expression, we see that delta x will cancel, and sigma and the force applied will be equal to 2 sigma L, and sigma will be equal to a force divided by 2L. So 2L is the total length of this boundary, of the film boundary. It's the total length. That is, if we take into account the length of the upper boundary, the upper surface, and the length of another surface which is from opposite side. So 2L is the total length of the boundary. And so the force applied to this slider divided by the total length is sigma. Therefore, this formula gives you another physical sense, a physical reason behind this quantity of surface energy. This can be interpreted as the force acting on a unit boundary length of a thin film, on a unit boundary length. That's why it also has this particular unit of measurement as the newtons, the unit of measurement of force, divided by meter, unit of length. That has a physical sense, as this example shows. So now I would like to consider a small problem related to this material. I have chosen to consider problem from Landsberg course of elementary physics. Yes, the problem from Landsberg course of elementary physics. And that is problem 14.3.3 from Landsberg. It's not from our collection of problems, but the different source. So the problem reads, what work must be done to spray 1 kilogram of pure water at 20 degrees Celsius into small drops having a diameter of 1 micron? So we have a mass of water given to us, 1 kilogram of pure water, and we want to spray this amount of water into small drops, each drop having a diameter of about 1 micron. 1 micron, which is by definition 1/1,000,000th part of a meter. The initial surface of water is small as in comparison with the total surface of all drops, but that we will see that is true. And what amount of heat will be liberated if all the drops merge into one, the temperature remaining unchanged? So we have 1 kilogram of water, which has the volume of 1 liter, and we plan to spray this water into small bubbles. The only thing I need to solve this problem, I need to know the surface tension of water. The surface tension for water is 0.0725 in the international system of units, which is, we mentioned already, joules over meter squared. That is the surface tension of water, which can be measured. By the way, the method of measurement I think we will discuss later today. The methods of measuring the surface energy. And so we have 1 liter or 1 kilogram of pure water, and we know the surface energy of water, and we need to calculate how much energy should be spent in order to spray this amount of water, 1 kilogram of water, into small droplets, about 1 micron in diameter. Each small droplet is about 1 micron. So, what is the surface energy? And what is the total? The surface energy, by definition, is the energy of a unit area of a liquid surface. So, in order to calculate the total energy needed to create so many small droplets, we have to use the formula which relates the total energy and the surface energy and the total surface area of all the drops, all the droplets of such small diameter. So that will be, what is the surface area of 1 droplet? If we know the diameter, and we know it approximately, because it's obvious that not all the droplets will have the same diameter. So we may use some approximate formulas to approximate the answer. The surface of each droplet may be assessed or estimated as its diameter cube. The surface of each droplet may be estimated as diameter squared. Diameter cube will be the volume of each droplet. So diameter squared will be the surface of each droplet. And now we have to multiply the surface of each droplet, the area surface, by the number of droplets. How can we assess the number of droplets? So sigma times d squared remains where they were, and we have to assess the number of droplets. What will be the number of droplets? 1 liter is such a volume which is 1 decimeter, the cube volume, cubical volume with 1 decimeter, the size of this cube. So this is 10 centimeters. And if we try to calculate the volume, that will be 10 centimeters cube. And the volume of each droplet, I will take it as a small v, is about its diameter cube, approximately, by the order of magnitude. I don't need to calculate all these things like 4/3 pi radius cube. Well, I don't need all these sort of things because I calculate only by the order of magnitude, because this is just an assessment. It's obvious that all the droplets may have different diameters and no precise calculation is possible. So we assess the result by the order of magnitude. So by the order of magnitude, that will be the volume of one droplet, and that is the initial volume of all water. So if we divide capital V by small v, we obtain the number of small droplets which can be obtained, which can be produced by sprinkling all this amount of 1 kilogram of water. So the number of droplets can be estimated as the initial volume of water divided by the volume of each droplet. And that will give us sigma d squared. Initial volume is given. It's just 1000 centimeters cube divided by d cube. And that will give us, now we will substitute the numerical values, and we have to take this value which is given to us 0.725 in the international system, and here we will have diameter squared cancelled with diameter cube, and only one diameter will remain in a denominator, and so we will have 1000 centimeter. I draw your attention to the fact that we now use centimeters instead of meters, so we have to be very careful at this place. This is not coinciding with international system unit. It's not a meter, it's a centimeter, 100 times smaller, and the diameter of is 1 micron, so it's 1/1,000,000th part of a meter. And if we take a centimeter, it will be 10 to the minus 4 power of centimeter, and this is centimeter cube. And so what we have here, 10 to the 3rd power, 10 cube, and 10 to the power of 4th, we will have 10 to the 7th power. So we will have this number, and how many times the decimal point will jump? 7 times. 1, 2, 3, 4, and another 5, 2, 5, 6, 7. Another 3 zeros will be here. So it will be 7, 2, 5, 3 zeros. That's, I multiplied this small number by 10 to the 7th power, and what we have in the units of measurement, we must be very careful with the units of measurement. That is joule over meter squared, and here we will have only centimeter squared. If I forget about different units, I will be mistaken. The mistake will be 10,000 times, because there are 100 centimeters in 1 meter, and so 1 centimeter divided by 1 meter is 10 to the power of minus 2, and if squared, that will be 10 to the power of minus 4. a centimeter squared is 10 to the minus 4 meters squared. So instead of centimeter squared, I can substitute this quantity, and then meter squared will cancel. Meter squared will cancel, and only joules will remain here. And that's what we need, because we need to calculate total energy, and total energy is measured in joules. That will be the correct units of measurement. And what we have as a result of all these calculations, we'll have to multiply this figure by 10 to the minus 4 power. And so here will be the decimal point, 72.5 joules. That's the energy needed to be spent. We need to spend so much energy to spray 1 kilogram of pure water into small droplets of small diameter, about 1 micron diameter. So what is this? What is this energy? Can this energy be somehow imagined so that you feel what amount of energy? You remember that a joule, 1 joule is 1 Newton per meter. So if you take 1 Newton force and apply this force on the distance of 1 meter to move some object with this force, then you perform the work of 1 joule. So 75 joules, if you remember that 1 kilogram force is 10 newtons. So if I take 10 newtons here, then I can say that 72 joules is the work performed by a force of 7.25 kilogram forces on the distance of 1 meter. So you apply a force of 7 kilograms, and using this force you push some object at the distance of 1 meter. That's quite a considerable amount of work from our everyday experience. Well, that's quite a reasonable amount of work which has to be performed here in order to spray 1 kilogram of pure water into small droplets. That's the solution of this problem. I think that is interesting. It shows that in order to spray water into small droplets, you need to perform some considerable work. Why? Because small droplets will have a large surface area, and surface has the surface energy. And in order to create surface, you have to spend energy, you have to perform work. That's why we need that amount of energy to spray water into small droplets. And another thing I would like to consider today will be a pressure inside air bubbles in water. So suppose we have a vessel filled with some liquid, not necessarily water, and there is an air bubble inside it, and the air bubble has radius r. And the surface of this air bubble is the surface of liquid, and the surface of liquid has some energy, and also we must apply some force in order to increase the surface of the area of the liquid surface. So all this tells on all this influences the pressure inside the bubble. So I will draw this bubble on a larger scale, so that we can easily see what happens here. There is some pressure outside the bubble, let it be P1, and there is some pressure of gas inside the bubble, let it be P2. And suppose the radius of the bubble is slightly increased. So we move the surface of the bubble and slightly increase the radius. We increase the radius by this amount, delta R. If we increase the radius, then we increase the volume of this bubble. We increase the volume. And when we increase the volume, we know that some amount of work is performed on the gas or by the gas. It's performed by the gas. And this amount of volume is the pressure difference inside the gas and in the outside area, in the outside region. Pressure difference times change of volume. Any change of volume is associated with the work performed by the gas. And this work goes to increase the surface energy. The surface energy is given by this formula. So that will be the increase in surface energy, which will be just sigma delta S, which is the increase of the surface. So we imagine that the radius of this bubble has slightly changed. And we are sure that in this case, such work is performed by the gas inside, and this work goes to increase the surface area. Because there is some energy associated with the surface of liquid. So that's the main idea of calculations, and we just have to carry out calculations of every physical quantity contained in this formula. First of all, delta V. What is the volume? The volume can be, delta V can be approximately calculated as the area of the surface, which is 4 pi radius squared, times the height of this layer, delta R, the area of the sphere surface, the area of the sphere surface, times the height of this, or the thickness of this thin layer, delta R. That will be the change in volume, because we need this volume to calculate, to assess this volume. And also we need to assess the change in the surface area. Well, that will be 4 pi. The final surface area will be R plus delta R squared minus the initial surface area, which will be R squared. And if we open this round bracket, well, let's do it. That will be R squared plus 2R delta R plus delta R squared minus R squared. So we open this round bracket squared, we obtain this formula minus small r squared. R squared is cancelled in this formula, and delta R is so small that it can be neglected in comparison with the radius. So what remains here is 4 pi times 2R delta R. So after substituting these results into our formula here and here, we obtain pressure difference P2 minus P1 times 4 pi R squared delta R should equal to sigma, the surface energy or surface tension, times this quantity, which will be 8 pi r delta r. In this formula, delta r will cancel, r will cancel, one r will cancel here, and a single r will remain here. Pi will cancel, and what remains here? The pressure difference, P2 minus P1, will be 2 sigma 8 divided by 4 is 2 sigma divided by the radius. That's the final formula we obtained for the pressure inside the bubble, and we consider an air bubble inside the liquid. The pressure inside the air bubble which is immersed in liquid. So the pressure difference is always positive. It means that the pressure inside the bubble is larger than the pressure of liquid near the bubble. And the pressure difference is defined by this surface tension quantity sigma, and it's inversely proportional to the radius of the bubble. It means that the smaller the bubble, the higher the pressure is inside. The smaller the bubble, the smaller the radius of this bubble, the higher the pressure will be inside the bubble. Now suppose you have a foam of soap solution in water, and the foam consists of many bubbles, and one bubble, and here is another bubble, and another bubble maybe, and so on and so on. And there is some surface inside, and the foam of soap solution, which can easily be obtained when you wash your hands with soap, consists of such small bubbles. Each bubble has a surface, and there is a surface energy and surface tension, or surface tension on the surface of each bubble. And so the same considerations which we described and discussed above are applicable to the soap foam, and the bubbles in the soap foam. And so the pressure inside the bubbles is larger than the atmospheric pressure, and the pressure in a small bubble is larger than the pressure in a large bubble. And all these phenomena are described by the formula which we just obtained, with the only difference that the soap bubble has two surfaces, inside surface and outside surface and inside surface. And therefore, each surface will make its contribution to the pressure difference. And as we have two surfaces, the contribution of two surfaces will be double the contribution of a single surface. So for a foam bubble, the pressure difference between the pressure inside and the pressure outside the bubble, pressure inside the bubble and pressure outside the bubble, will be given by the same formula multiplied by 2, so it will be 4 sigma over the radius of the bubble. Here we have 4 instead of 2 because there are two surfaces of the bubble, the outside surface and the inside surface. Let's consider problem number 362. A problem so the problem is this. Problem 362. A soap bubble with a radius r is placed on another bubble with a radius capital R. So there is a bubble of large radius capital R, and a small bubble is placed on a small bubble with radius small r is placed on a large bubble. What will be the form of the soapy film separating the two bubbles? So there is inside a surface, there is a thin film separating these two bubbles inside, and we need to find the form or the shape of this soapy film separating the two bubbles, and also what angles will be formed between the films at the points of contact. So what angle is here if we draw a line tangent to the surface of the large bubble, and another line tangent to the surface of the small bubble, and another line tangent to the inner surface between the two bubbles? What will be the angles? What angles will be formed between the films at the point of contact? Well, so we need to find this angle, alpha, and we need to find the radius of curvature of this surface of thin soapy film, thin film between the two bubbles. So this radius of curvature, we need to find it. Let it be x. We don't know the radius of curvature of this surface, the surface separating the two bubbles inside them. So what shall be the equations? What's the idea to solve this problem? The idea is that the thin film here between the two bubbles is in a position of static equilibrium. So the pressures, the pressure of atmosphere inside the large bubble and inside the small bubble should somehow be related with the condition which we have just derived, which describes the difference of pressures. So let the atmospheric pressure be P0, and the pressure inside the large bubble P1, and the pressure inside the small bubble P2. So we can say that the difference between P1 and P0, the difference between pressure in the large bubble and atmospheric pressure, is defined by the surface energy of the soapy film, and the film has two surfaces, the outside surface and the inside surface. So there are 4 sigma divided by the capital R, the radius of this large bubble. Similar condition should be applied to the pressure inside the small bubble. The pressure inside the small bubble minus the pressure, atmospheric pressure, should be equal to 4 sigma divided by the radius of the small bubble. And similar conditions should satisfy the difference of pressures between these two bubbles, that is, pressure P2 minus pressure P1 here must be 4 sigma divided by the radius of curvature of the surface of the film surface between the two bubbles, that is, divided by x. So we have some system of equations, 3 simultaneous equations that may be easily solved. to find x. First of all, we can find P0 from, we don't need it, we don't need P0 for the final answer. We need to find x, and we don't need P0, so we may subtract first equation from the second equation, and we will have, if we subtract first equation from the second equation, we will have P2 minus P1, that is this P2 and this P1, and P0 will cancel, and then we will have that equals 4 sigma divided by small r minus 4 sigma divided by capital R. And this difference between the pressures in two bubbles can be expressed through the last equation, which is 4 sigma divided by x. Using this relationship, we can find x. First of all, we notice that 4 sigma can be cancelled, and what remains here, we can immediately find x as capital R small r divided by capital R minus small r. That is the answer for the radius of curvature of the film surface between the two bubbles in a soapy film, in a soapy foam. Now the second question, how to find angle alpha. We know that surface energy sigma, this surface energy sigma, is not only the energy of a unit area of the surface of liquid, but it's also a force which is applied to a liquid boundary, to a unit length of liquid boundary. So here is the boundary of liquid surface of one bubble and another bubble, the large bubble. This is the boundary between them, and to each small element of this boundary there is a force applied, a force acting on this small boundary, a small element of boundary. And so some force acts here, and another force is acting from this film, and another force is acting from the inner film. And all these forces, as we have already obtained, all these forces can be calculated as 2 sigma divided by 2L, or sigma divided by L, 2 sigma divided by L, because there are two surfaces. So the sigma, the surface energy or the surface tension, is the same. The same liquid forms all the bubbles here. So sigma is the same. And the surface element, the boundary element, is also the same. It means that forces acting from in all the directions here along the thin film's surfaces, the forces are the same, are equal to each other. And therefore we can easily understand that the condition of static equilibrium of this point means that if equal forces are applied, the angles must be equal. That will be the same, the 3 equal angles. And as the total angle is 360 degrees, then each angle alpha is just 120 degrees. That can be put as 2 pi over 3. The total angle of 360 degrees, we divide by 3 and obtain the angle alpha, 120 degrees. So whenever you see a soapy foam, a foam formed by a soap solution in water, when you wash your hands, for example, you can easily obtain such a foam. You see many, many bubbles there in this form, and you may be sure that this angle between the surfaces of two adjacent bubbles is always 120 degrees. And we have another 1 or 2 minutes, and I would like to mention the last property of liquids which we must discuss, and you must read about it in the textbook and make sure that you understand it. It is the notion of wetting and non-wetting of water and a solid surface. So if we have some liquid and we immerse a very thin capillary tube here, very thin capillary tube, then what will be the peculiar properties of the contact between water and the walls of this tube? You may understand that if a glass tube is immersed in water, then the surface here is not exactly flat. The surface here takes this form, and also water will go up at some height, and the surface here will also have some radius of curvature, and that will be the height to which the water will go into the small capillary tube. So this is a side effect which is caused by the interaction of molecules of water and molecules of solid body, a glass tube in this case. There is another possibility. If you immerse similar tube into, I will deliberately show it at larger scale. If you immerse a similar tube into a different liquid, and I will suggest that we take mercury. If you immerse it into mercury, then you will observe that the surface of mercury is such, it takes a different form, and also the mercury will go, also the mercury will fill just part of the tube. It will not go up to the surface, and it will not go higher than the surface of liquid as in the case of water. This is water, and this is mercury. So the shape of the surface will be defined by approximately some spherical shape having some radius of curvature which coincides with the radius of this tube. And so all these phenomena are due to wetting or non-wetting. We say that water is wetting the surface of glass, and mercury is not wetting the surface of glass. So in this case we have wetting of glass by water, and in this case we have non-wetting of glass by mercury. And so the behavior of a liquid in such small capillary tube is different. Well, as we have no more time to discuss this issue, I would like to urge you to read about it in the textbook of Landsberg. It's quite clearly, everything is explained clearly in this textbook. And also I would like to announce that my students will receive later today, a message explaining how they will defend their first home assignment. That about this procedure I will inform you later today. Thank you. On this point, let us finish the lecture.